Hey guys, for any switching application, MOSFETs are widely used. To get the highest efficiency out of it, we need to increase its switching speed. That is by increasing the turn on speed and turn off speed. We can use some external circuits apart from MOSFET gate driver and gate resistor, which are known as speed enhancement circuits for faster switching. And in this video, we are going to learn about those circuits. So let's start. When speed enhancement circuits are mentioned, we should exclusively consider circuits that speed up the turn-off process of the MOSFET. The reason is that the turn-on speed is usually limited by the turn-off or reverse recovery speed of the rectifier component in the power supply. The fastest switching action is determined by the reverse recovery characteristics of the diode and not by the strength of gate drive circuit. This is the most famous misconception. We have seen in our previous video about the limitation of switching speed and the significance of the gate resistance. Please click on this card above to know more about it in detail. We can apply a higher permissible voltage across the drive output impedance and the gate resistor to get the optimum turn-on speed. So usually the obtained turn-on speed while switching is sufficient to drive the MOSFET. But the situation is very different at turn-off. In theory, the turn-on speed of the MOSFET depends only on the gate drive circuit. If we take a higher current turn-off circuit, it can discharge the input capacitor of the MOSFET quicker, which provides shorter switching times and consequently lower switching losses. This higher discharge current can be achieved by a lower output impedance of the MOSFET driver. While faster switching can potentially lower the switching losses, but when we increase the turn-off speed, ringing in the waveform occurs due to the higher turn-off, change in current with respect to time, and change in voltage with respect to time of the MOSFET. This is something to consider in selecting the proper voltage rating and EMI containment of the power device. Well, we'll focus on the techniques which increase the turn-off speed of the N-channel MOSFET when it is used as a low side switch. The easiest way to increase the turn-off speed is by using a turn-off diode. In this circuit, the gate resistor allows adjustment of the MOSFET turn-on speed. During turn-off, the antiparallel diode bypasses the resistor. We'll name it as D-off. This D-off works only when the gate current is higher than this formula, which is the VD-off upon the gate resistance. Typically, for 150 mA gate current, we can use 1N4N48, and for around 300 mA current, a BS40 Schottky antiparallel diode can be used for faster switching. As the gate to source voltage approaches 0 volts, the diode helps less and less. Because of that, this circuit provides a significant reduction in the turn-off delay time. The disadvantage of the circuit is that the gate turn-off current flows through the driver's output impedance. Before going to the next topic, I have a very small request. You know, only 13% of the viewers have subscribed to my channel. Come on guys, you're watching my videos, which means you love my content, and I need your love and support, which motivates me to make more such amazing videos. So please subscribe to my channel. Now, the next is PNP turn-off circuit. This is the most popular arrangement for turn-off speed enhancement. The construction of the circuit would be like this. The circuit works as intended during the turn-on process. The current flows from the gate resistor and this diode. During the turn-off process, this gate driver provides a low signal at the output. Due to that, this PNP BJT turns on and the gate and source get shorted locally at the MOSFET terminals, which discharges the charged input capacitor of the MOSFET. Gate resistor limits the turn-on speed, and this diode provides the path for the turn-on current. Also, it protects the base emitter junction of the PNP BJT against the reverse breakdown at the beginning of the turn-on process. The most important advantage of this solution is that higher peak discharge current of the MOSFET input capacitance is confined in the smallest possible loop between the gate source and collector emitter connection of the two transistors. Also, the turn-off current does not go back to the driver. It does not cause ground bounce problems, and power dissipation of the driver is reduced substantially. The turn-off transistor shunts out the gate drive loop inductance and output impedance of the driver. Furthermore, this BJT never saturates, which is important to be able to turn it on and off quickly. If we take a closer look at the circuit, we would get to know that the solution is a simplified bipolar totem pole driver, where the NPN pull-up transistor is replaced by a diode. Similar to the totem pole driver, the MOSFET gate is clamped by the turn-off circuit, eliminating the risk of excessive voltage trace at the gate. The only known shortcoming of the circuit is that it cannot pull the gate all the way to 0 volts because of the voltage drop across the base emitter junction of PNP BJT. The next circuit to examine is the local NPN turn-off circuit. Similar to the PNP solution, we can use NPN BJT. We'll call it as Q1. In this case, the gate discharge current is well localized. The NPN transistor holds the gate closer to the ground than its PNP counterpart. Also, this implementation provides a self-biasing mechanism to keep the MOSFET off during power-up. Unfortunately, this circuit has some significant drawbacks. The NPN turn-off transistor Q1 is at inverting stage. It requires an inverting PWM signal, which can be provided by another transistor Q2 as shown in the circuit. Again, the turn-off process is the same, but when we need to turn off the MOSFET, this BJT should turn on. So, this inverter circuit draws excessive current from the driver during the on time of the MOSFET, which decreases the efficiency of the circuit. Furthermore, Q2 saturates during the on time, which can prolong the turn-off delay in the gate drive. So, all of these turn-off circuits which are shown here have simple ground reference to the gate drive circuits. Well, if we summarize all of these three circuits, the PNP BJT based solution to enhance the turn-off switching speed is the most optimum and widely used. If you want a low-cost circuit, we can just use the turn-off diode. Third circuit is complicated and has so many components. I would keep my hands away from it until it is highly required. So, that's all about how to increase MOSFET switching speed. I have added all the references related to these circuits in the description. If you have any query, you can ask me in the comment section or email me. Hit the like button and subscribe to my channel. And finally, thank you so much for watching this video.